for improper integrals. So, it is allowed in this case. So, you will pull out a log t squared, double differentiation will produce a log t whole squared. And so, the second derivative is positive, and so half is a local minimum. It is also a global minimum, that I am leaving it as an exercise to show. So, as a first lemma, let us prove that b of a equal to integral 0 to 1 x to the power a minus 1 plus x to the power minus a upon 1 plus x, which is equal to 1/2 of integral 0 to infinity x to the power minus a plus x to the power a minus 1 upon 1 plus x. Please write just this equation, that is all that you need. B of a equal to integral 0 to 1 x to the power a minus 1 plus x to the power minus a upon 1 plus x dx, which is the same as 1/2 of integral 0 to infinity x to the power minus a plus x to the power a minus 1 upon 1 plus x dx. This is very easy to prove, and rather than write out all these things, you just write this down and take it as an exercise, correct. You have to break the integral from 0 to infinity as an integral from 0 to 1 plus an integral from 1 to infinity. In the second integral, put x equal to 1 over t, that is the obvious thing to do. So, this is proved, lemma 1 is taken care of. So, have you written down the equation? Just the equation and nothing else, that is all that we really need from lemma 1, all right. Let us keep this on the side. Now, let us go to lemma 2. Again, just write these two numbers, these two equation number. B of a, w of a minus 1 equal to integral 0 to infinity x to the power a minus 1 dx upon x plus w. The second one is b of a, w to the power minus a equal to integral 0 to infinity x to the a minus 1 dx upon 1 plus x w. Proof is again trivial, put x equal to t w and put x equal to t by w respectively. That is it. Proof is pretty trivial. Now, go back to that lemma 1 which you have written down. Write just these two equations 1 and 2. How it comes about is pretty trivial. Simple change of variables, right? No need to write the change of variables and all, you can figure it out. Now, go back to lemma 1. What does lemma 1 suggest? Lemma 1 suggests that we should add 1 and 2. Lemma 1 suggests that we should add 1 and 2 and divide by w plus 1. Look at that equation, it's right, you have written it down from lemma 1. The slide is gone, but you have it written down, correct. So, if you do this, what are you going to get? You are going to get this particular equation over here, this one, b of a into integral 0 to infinity w of a minus 1 plus w of minus a upon 1 plus w dw equal to, now when you add up this and this, that x to the power a minus 1 is a common factor and rest are the things that are involved that involve w that have been taken in the second one. This integration you can actually perform, no? You can actually perform this integration. If you take the, if you simplify this, rational function, the w plus 1 will cancel out, you can check it directly and you can it's a logarithm that appears and this is the equation that you are supposed to check. But what is this? What is on the left hand side? Go back to lemma 1, it is simply b of a the whole squared. So, we get the very interesting equation. Please write down equation number 3, b of a the whole squared equal to integral 0 to infinity x to the power a minus 1 log x upon x minus 1 dx. We have got a third equation. Blanket exercise, all improper integrals you have to check the convergence, okay, every one of them. So, you get the equation b of a the whole squared equal to integral 0 to infinity x to the power a minus 1 log x upon x minus 1 dx. Alright, so keep this 1, 2, 3 in mind with you in front of you. That is why I said do not write too many things, so that you just have the 3 equations that you need right there. If you write too much, then there is too many things and you have to search back and forth. Now, I had in this slide you again see 1 and 2 for your convenience. Is there in your notebook and it is there in the first 2 lines, no need to write it again. Subtract 2 from 1, subtract 2 from 1, and what do you get? You get b of a into w to the power a minus 1 minus w to the power minus a upon w minus 1. Subtract and divide, subtract and divide, equal to integral 0 to infinity x to the power a minus 1 dx into 1 minus x upon x plus w into 1 plus xw. That 1 plus x comes from simplification, nothing else. 1 plus x simply comes from simplifying the rational function, that is all, correct. Do not be puzzled about this 1 minus x, nothing mysterious, just algebra, plain algebra, that is all. Now, integrate from 0 to infinity and you get b of a into integral 0 to infinity w to the a minus 1 minus w to the power minus a upon w minus 1 dw equal to integral from 0 to infinity x to the power a minus 1 log x upon 1 plus x dx. So, this integral you have to perform and you get this, alright. Now, the left hand side is also equal to, okay, excuse me, look at the right hand side. What is b again? Let me write down b for you. Remember what is b? B is integral 0 to infinity, yeah, x to the power a minus 1 upon 1 plus x dx, correct. So, what is this integral really? What is this integral? db by dA, correct. So, let's write this also. Write this last line. Correct? All right. Just write the last line, do not write anything else. But remember, one of the equations that you wrote down was BA squared. Remember? Do you have it written down? BA squared equal to integral 0 to infinity x to the power a minus 1 log x upon x minus 1. Have you written it? Now integrate this from 1 minus a to a. Instead of a, you take it as t, right? So bt squared equal to integral 0 to infinity x to the power t minus 1 log x upon x minus 1 dx, correct? Integrate it from 1 minus a to a. What happens when you integrate x to the power t minus 1? What is the integral of x to the power lambda, d lambda? It is x to the power lambda by log x, and the log x and the log x will cancel out, correct? So, compute the definite integral 1 minus a to a bt squared dt. It works out to be exactly this, correct? Well, the log x in the numerator got cancelled while integrating. Integration with respect to t produced a log x in the denominator, and it's a definite integral from 1 minus a to a. That is how you get all these things, correct, right? You have to do the algebra. It is a simple integration, just one single integration, that is it, nothing complicated. But now multiply this equation by b of a, multiply this equation by b of a and compare it with one of the equations that you have got earlier, the db by da, remember? You see this equation 4 coming out now? You wrote down that expression for db by da, no? And that is exactly this. So, you see equation 4. Please write down equation 4. Just write down equation 4, that is all, or reference, otherwise you will have to keep searching. Now, what do you know about BA? It is symmetrical about the point half. So, either I can restrict it to 0 half or half 1, does not matter, take your pick, it really does not matter, it makes no difference. So, let us stick to 0 half or let us stick to half 1, later on we will need half 1, so stick to half 1. And differentiate equation 4 with respect to a. Remember, we have discussed in detail how to differentiate an integral. Integral alpha x to beta x f of x comma t dt. Leibniz rule for differentiating an integral. Remember, we have discussed it in great detail. Apply the rule. Apply the rule here. Differentiate it. There are going to be two terms, beta prime of a into integral 1 minus a to a bt squared dt plus ba into the derivative of this. There will be how many terms? 3 terms, but no term coming from inside. So, there will only be 2 terms, correct. The integrand does not involve an a, thankfully. There will only be 2 terms, one of them is ba squared, other one is b of 1 minus a the whole squared into minus 1. Remember that you have to differentiate, you are using chain rule. And that produce a minus 1 here, and b of a is the same as b of 1 minus a, correct. And right hand side gave you what? 2 times, we have looked at the left hand side, right hand side gives you 2 times d2b by dA squared, correct. You got this. Now, multiply by b of a, multiply this equation by b of a and remove this integration term. Multiply this equation by b of a and use equation 4 to get rid of the integral term. The integral term, after differentiating, the integral term persists, no. So, get rid of it, use equation 4 again, multiply by b of a. What will come? B of a into b of a into b prime of a into this. So, b prime will remain, b into this will be 2 db by da, correct. Alright, let us see what we get. We get this 2b prime squared, right, 2b prime squared plus b squared into b of a squared plus b of 1 minus a squared equal to 2b double prime. No need to write all the intermediate steps. B of a is the same as b of 1 minus a. So, those two things will combine and that will also produce a factor of 2, and the true can be cancelled out. So, write down just the ODE 5, b prime squared plus b to the power 4 equal to bb double prime. Correct. And we have initial conditions, b of half is pi, b prime of half is 0. We have a second order ODE with two initial conditions, and hopefully we can carry out the whole exercise of computing BA uniquely. Now you understand why I chose Dedekinds proof to present in an ODE course. It is a very ODE based proof. Ultimately, we are trying to derive an ODE for the function b of a. It turns out to be a non-linear second order ODE. Fortunately, a does not appear explicitly in this equation. That is a great simplification. Correct. Now, this differential equation actually can be integrated. Now, remember that b prime is positive. Remember, half is a global minimum. So, the graph is like this. So, from half to 1, b prime is always positive. So, it is a strictly increasing function on the open interval half 1. So, it is an invertible function. So, I can express a as a function of b. B is a function of a. So, I can invert this and think of a as a function of capital B. And then the derivative, let us call the derivative c. The derivative is a function of a, but a is a function of b. So, b prime becomes a function of b. Let us call b prime as c, just for simplicity, it looks much nicer that way. So, now let us apply the chain rule. B double prime equal to dc by dA equal to dc by d capital B into d capital B by dA. It is exactly for performing this chain rule that I must worry about the invertibility of the relation of the function B. But dc by dB is, keep it as it is, and dB by dA is c. So, b double prime is nothing but c dc by dB. Put this into the differential equation. The ODE becomes c squared plus b to the power 4 equal to bc dc by dB. It is a Bernoulli equation. Wonderful. Or you can write c dc by dB as d of c squared by 2, and it becomes a linear ODE in c squared, first order linear ODE in c squared. And you want initial conditions, you have them when a equal to half, b equal to pi and c equal to 0, correct? Alright. So, you have to solve the first order linear ODE and you get your c. Well, you get c squared equal to b squared into b squared minus pi squared, putting the initial conditions, right. Now, c is positive on the range half to 1. So, you are supposed to take the positive square root, right. Pi is a global minimum. So, b is going to be greater than pi except at half, when it is going to become equal to pi. So, you have to take the square roots, you have to settle the sign of the square root, that is why all this stuff. So, c is finally b root b squared minus pi squared, but what is c? dB by dA, variable separable equation. Variable separable equation, you have an initial condition at half. So, you can solve it. Correct. We get b equal to pi cosecant pi a. So, the gamma a into gamma 1 minus a is pi cosecant pi. Remarkable derivation, absolutely remarkable, tour de force as they would call it. Well, the next few minutes that is left, about 10 minutes, let us go to the next remarkable formula of Gauss, the product formula of Gauss. Gamma z equal to limit as n tends to infinity, n to the power z n factorial upon z into z plus 1 into etc. z plus n on the real part of z bigger than 0. So, you see that all the principal properties of the gamma function are being derived completely in this course, correct. All right, we want to prove this. How do you begin? Begin with the integral definition, gamma z equal to integral 0 to infinity e to the power minus t to the power z minus 1 dt. And here the only trick is to replace the exponential function e to the power minus t by limit as n tends to infinity 1 minus t by n raised to the power n, and replace 0 to infinity also by the finite interval 0 to n. Of course, you have to justify this step. That is always hard, right? Passage to limit under the integral sign has to be justified. That is always difficult, but anyway, let us hope that nothing goes wrong. Let us hope that it is correct. Let us hope that this replacement is a legal replacement. The legalities can be discussed later. Let us just proceed formally and integrate by parts. Write t to the power z minus 1 as d dt of t to the power z by z and integrate by parts. What do you get? D dt will go from that term to this term. There will be a boundary term, right? What will be the boundary term? At 0, which will go, t to the power z by z is there. So, at 0 it will go, and at n what will go? The other term 1 minus t by n raised to the power n, that will disappear. So, there will not be any boundary terms left after you perform integration by parts, correct? Alright. So, that is exactly what you get, gamma z equal to limit as n tends to infinity 1 over z 0 to n 1 minus t by n to the power n minus 1 t to the power z dz. Correct. Well, I am going to go ahead further and integrate by parts over and over again successively. Successive integrations by parts gives you gamma z equal to limit as n tends to infinity. Each time you differentiate, you are going to pull out an n minus 1 as a coefficient, and n minus 2 and n minus 3. That is how the n minus 1 factorial term comes out, correct. And each time you differentiate, you have to use chain rule, that t by n, that is going to produce an n in the denominator. That is how the n to the power minus n minus 1 is going to come. Each time you integrate by parts, the t to the power z will become t to the power z plus 1 etc., and those exponents are going to come in the denominator. So, you get this wonderful thing, n minus 1 factorial n to the power minus n minus 1 upon z into z plus 1 into z plus 2 into etc., z plus n minus 1 integral 0 to n t to the power z plus n minus 1. Because you see the other factor is a polynomial, right? 1 minus t by n to the power n minus 1 is a polynomial. So, n minus 1 integrations by parts, the polynomial will just become a constant. After that, there is no need to integrate parts further, you can actually finish the thing. So, finish it off and you get the product formula of Gauss. What remains? To justify the principal step, the very first step, right? Okay. Is it clear? Shall we proceed? Okay. So, let us assume that z is real positive. Let us justify it for the case of z real, and then the usual trick, both sides are analytic on the right half plane and they will agree at the positive real axis, so they will agree everywhere. That is a standard trick. What is the monotone convergence theorem from analysis? The monotone convergence theorem says that if you take a sequence of, say, continuous functions, let us stick to continuous functions because that is all that we really need here. You have a sequence of continuous functions which are non-negative, 0 less than or equal to f1 less than or equal to f2 less than or equal to etc. And the sequence converges pointwise to f, then passage to the limit under the integral sign is justified. This is the monotone convergence theorem. Normally you will see it in the context of Lebesgue integrals, and that is the way to do it. Lebesgue theory gives you a clean proof of this theorem, and that is the way one should do it. If you have not studied Lebesgue theory, assume this theorem. You can assume that the functions are continuous, so that the measurability issue can be forgotten because our functions are actually continuous. They are even better than measurability. Correct? This is the monotone convergence theorem, and so we should apply the monotone convergence theorem to carry out our justification. So what do? You take f of n to be, what is the function that we are looking at? 1 minus t upon n to the power n times t to the power x minus 1. Remember, z is real now, so I have taken x times the characteristic function of 0 to n. Characteristic function of 0 to n, right? Clearly the thing is positive, non-negative, okay. And then what are we supposed to check? Fn less than or equal to Fn plus 1. That is, we have to show that, and we need to worry only about the interval 0 to n, right? Because on n to n plus 1, Fn is 0 and Fn plus 1 is positive, finished. So the job is relevant only in 0 to n, and this is the thing that you have to prove. What is the standard trick? Calculus. You will differentiate 1 minus t by a to the power a with respect to a and show it is positive. Do it, I will leave it to you as an exercise, correct? Alright. So that will complete the justification because the monotone convergence theorem can be applied and the passage to the limit under the integral sign is justified. So that completes the proof of the Gauss product formula. Why is the Gauss product formula important? Let us look at a simple corollary of it. The immediate corollary from the Gauss product formula is this. When you put x z equal to half, you get the Wallis product formula, right? You get the Wallis product formula. Good. You get the Wallis product formula. Another corollary is to obtain the factorization for the sine function. Another fact, just write down these expressions. Don't spend too much time in copying down. Correct. Okay. All right. Finished writing? Please copy down these things. The yes, good. Finally, our discussion of the gamma function will be incomplete if I do not mention the very important result called the Stirling's approximation formula. I am sure you must have seen the Stirling's approximation formula somewhere, for factorials at least. It is one of the most important formulas because whenever you work with large particle systems, statistical mechanics, etc., you need to approximate factorials of large numbers by exponentials. But after all, the gamma function is a generalization of the factorial. So, one can ask whether there is a Stirling's approximation formula for the gamma function. There it is in the very last line. Gamma of x plus 1 is asymptotic to x to the power x e to the power minus x square root of 2 pi x. I am stating it over the reals. There is a corresponding formula for the complex numbers. These will hold in certain sectors, but I am not going to worry about all those things. What does this tilde mean here? The ratio goes to 1. The ratio goes to 1 as x tends to infinity. The ratio goes to 1 as x tends to infinity. Correct? A very nice proof was given by Joseph Liouville, but unfortunately I really don't have time to discuss the proof of Stirling's approximation formula. I think we have to wrap up this discussion of the gamma function. And okay, shall I proceed? So now what's next? You know what's next? Large list of problems. Looking forward to it? Yes, I am so glad. Right? Copy these things down. Problem number 6. Yeah, I mean this is a new list you can think of. Tutorial 6, okay, fine. Tutorial 6, all right. Tutorial 6 is on beta and gamma functions. All exercises on beta and gamma functions. By the way, calling it tutorial 6 doesn't mean that I am going to discuss it on Monday. We are going to discuss it in the afternoon. Just don't, that way you will start cutting every tutorial into 20 pieces. Okay. Just quickly jot down these exercises. I have a 4-page list for you. Sorry, 5 pages, I made a mistake. And after writing all these exercises, we will be ready for tea. And so it is in your interest to write it fast, because the slower you write, the colder will the tea get. Yeah, I just didn't want to cut it short. I want to do the whole thing because a comprehensive discussion of the gamma function is very essential, particularly since you are teaching engineering and all those. It's in general important because differential, not just for ODEs. For example, if you are studying the asymptotic properties, see one of the important things that you will have to deal with will be asymptotic behavior of solutions. So in many of the formulas in asymptotic analysis, gamma function will appear. For example, it will appear in number theory, in prime number theorem, etc. When you want to discuss these things. So gamma function is very important. I mean I think it's essential to have a very complete account of it. Aries functions, for example, the asymptotics of Aries functions, it will appear. If you take the Aries equations, ODEs, y double prime minus xy equal to 0, and you study the behavior of the solution for large values of x, it will appear, for instance. It appears in the formula for the Bessel's functions, for instance. So it's important to have all these things at one place. Stirling's approximation formula, the beta gamma relationship, reflection formula, all those things. It's better to have it is very closely related to hypergeometric equations, for example. So when you study hypergeometric differential equations, you study what is called as a monodromy of the hypergeometric equation. There the gamma function appears. The monodromy was explicitly computed by Gauss. Next one. All right. I know you're anxious to have tea. I'm also anxious. I not even had breakfast. I hope you're not asked them to get tea and biscuits. Huh? I hope there's going to be something to eat. I'm more anxious than you to get to have a little bite. Prove that gamma prime z upon gamma z equal to limit as n tends to infinity. Yeah, maybe wait a minute. Just a minute before this should precede. Excuse me, I'm sorry. Prove that gamma of h equal to, this is very trivial. First part is very trivial. Change a variable, simple. Gamma h. This appears in Dirichlet, for example, Dirichlet's book. On lectures on differential on definite and indefinite integral in one and several variables. In those lectures, this appears somewhere. So please do these exercises on the gamma function seriously. It's okay to have an extra 5 minutes today because tomorrow is off, right? Tomorrow I am giving you 3 hours off and Professor Murali Srinivasan is giving you 3 hours off. So you should not complain having to stay back for an extra 5 minutes today. Right, don't discuss, don't. Others will get angry with you if you delay it. So you see something about log convexity of the gamma function here. Log convexity of the gamma function. Done? No? Okay. Page number 3. Gamma prime z upon gamma z equal to limit as n tends to infinity log n minus sigma j from 0 to n minus 1 over z plus j. ln of n here, natural log of n, natural log of n. Another unfortunate thing is I am not able to discuss modern developments like Fugled's theorem on the generalization of Villon's theorem. I don't think I am going to get time for that. But it's not bad. In 2 hours time, we have covered a substantial bit of gamma functions. There's much more than you normally encounter in books, no? Normally, with full proofs, all the results have been proved, except for Stirling's approximation formula. Shall we proceed to the next slide? Have you written down, or are you just saying yes, yes? All right, 60% done. Yeah, fourth slide, no? Yeah, this is from Whittaker and Watson. This last problem is from Whittaker and Watson. Whittaker and Watson is a timeless classic. It's a great book, and if your library doesn't have it, please order a copy. A Course of Modern Analysis by Edmund Whittaker and G.N. Watson. It's an absolute classic, and you can dip into it from time to time, and you will never. It's infinite supply of remarkable results in classical analysis. A great reservoir. And what is remarkable is that a book which is so heavily laden with formulas, you will hardly see any mistakes. And it was written at a time when LaTeX and everything was not available. And still, you see its precision, and the quality of writing is also very superior. Whittaker and Watson, Course on Modern Analysis. Course on Modern Analysis, Cambridge University Press. So if your library doesn't have it, please, Modern Analysis, Course on Modern Analysis. If your library doesn't have it, make sure to order a copy. See to it that a copy comes to your library. Okay. Last slide. This is also, the very first exercise is also from Whittaker and Watson. The first and the last are from Whittaker and Watson. Whittaker and Watson. This is also from in 8 are from 1 to 8. The number 8. What happened? No, it's not infinity. No, it's not infinity, it's 8. R by 3. Or you can J by 3. It's a dummy variable, no? I just copied the problem as it is in Whittaker and Watson without bothering to change the symbols. So that is the end of chapter 4. Now we will start Laplace transforms, not today, on Monday. Monday morning we begin with Laplace transforms. It will take us at least 2 sessions